Alright, time for another DraftPhysics.com. DebatePhysics.com also. But the debate is in this crappy form of redundant crap by obnoxious and arrogant jerks. And that's all there is. So, yeah, that's all we have to work with. And I'll just be proving again the point that you can't talk to these people. You explain it and they just ignore the explanation, pretend it's somehow obtuse and unavailable, and it's in your face and clear, in my opinion, crystal clear. But anyway, why do you keep using immovable brick wall? I don't keep using it, but yes, it's a very useful way to analogize. So why do you keep using an immovable brick wall as an example when we are talking about collisions between two movable objects? Well, we're not talking about movable objects, are we? We're talking about when something can't be moved or it can't absorb the energy. We're talking about not perfect Newtonian one mass against one mass. We're talking about a one mass against a 3, or 1 against a 5, or 1 against an 8. And there are different rules because they can't just transfer the energy. Yeah, they can't convert this motion into this motion, and vice versa. You can't convert very fast motion into motion. So the part that can't be converted is the velocity. That's the trick of it. Obviously, I think. Okay. Is obviously you can't have 5 units of energy and try to spread over, a big. So you have your units on a Ritz cracker. Okay. And now you got to spread the same stuff over an entire piece of bread. It's not going to be spread as thick. Can't do it. So that's the trick of it. And I think I illustrated that clearly. Now, I'll go a step further. I'll try to add some more clarification, but frankly, it's a waste of time, as you're demonstrating. You are belligerent to understanding conceptually what you're arguing against and what you have to find evidence to prove is wrong. Okay, and the argument is that an electron and a proton and they can combine and they can form something called the nucleus. Okay, and then there's electrons. Okay, nothing else, no protons out here on the outside. And the argument is being made is that these are like balloons. Okay, and they're in a circumstance where they will be essentially being pushed against a brick wall, and so they will do exactly as I analogized in the previous video. And so these atoms are in pressure. So you have some vision that it's a bunch of swirly crap. Now the real universe is something like this. They're all in positions, they're connected to each other, they're sharing electrons in specific locations, they're not doing any rotating or any other kind of crap. Okay. And the idea is atoms, are elastic. So you push on these electrons with other electrons on some other atom over here, combines, pushes on these atoms push on the electrons share the pressure, and the idea is if they can move all these atoms, then the atoms yield, they move. If they can't move all the atoms, that if this pressure doesn't just easily migrate to all the atoms, then it doesn't move, it's stuck, and the pressure increases. Okay, and as the pressure increases of the electrons, it's essentially creating that pressure in all directions. So it's resisting any further motion because the pressure is getting higher and higher and higher. And now this object is going to have to start feeling that back pressure. And the question is, which one will yield? And the argument is momentum tells us the thing with less momentum will yield. All right. So I should make it more connected to the mass. The thing with more mass, okay, that has more atoms to move, is less likely to move. The thing with fewer atoms to move is more likely to move. So once the aggressor stops and the pressure has reached its maximum, then there's only a question, which one has more mass if neither side is moved? and the side with more mass is going to move more, is the simple argument. I think it's simple. Yeah, I'm pretty sure it's simple. Yeah. So look, the argument is elastic is a tricky word, but the idea of it is that you can store the energy, and the idea is the storage part, not some instantaneous contact. And there's no such thing as instantaneous contact. The whole argument is that each bit of it is electrons and protons moving. So that's the real universe. The electrons and protons will decide which way it goes, and their rules is that yes, the electrons can build up pressure, and then you're just making the argument, where can the pressure as a practical fact go? And if the brick wall doesn't yield the rest of the atoms, then the pressure has to go one of these other ways. That's the simple argument. All right. Yeah, I think that's clear enough why I used a brick wall for the balloon. Was just to give the balloon its elasticity to duplicate the atom, and at the same time give its immovability, so to duplicate the fact that atoms come in gigantic masses, and gigantic masses aren't going to move, but they're still elastic. Yeah, I think that's clear enough. All right, continuing. All right, you can't pressurize a balloon by pushing it against an object without pushing the object as well. So again, you're saying that every time there's a pushing force. So just for the viewers, we did this, right? Now, I didn't draw this part because I didn't think it was any necessity to draw something so simple. But I could compress a spring, and then I could put a clamp on it. Just like that. I could just have a big spring, and I could just smash it into a small space, right? So I take this spring that's relaxed, and I put it inside that horseshoe. Now it has constant pressure, no doubt about it. Is anything moving? No. Is the energy going away? No. So why are you arguing with me about you can't or this bullshit? Of course I can. Okay, so I can create constant pressure against something, and it doesn't mean anything because the pressure has nowhere to go. The wall doesn't move. The wall doesn't use up the pressure. You can't use the pressure unless you move something. You have to move something. The electrons have to start moving like electricity, or you have to move the atoms. But you have to move material objects, either electrons and protons or the whole atoms. Those are your two choices. You have to move something material to use the energy up, in the sense of make it go somewhere else where it's going to do other stuff and push on other things and make other things happen. That's the whole point of what Newton and Descartes were saying, is that motion is just exchanged from object to object. Oh, fuck. All right, the pressure will push against objects on both sides with equal force. In most cases, but you do have to understand that the pressure will also be in waves, okay? So we know that you can cause a pressure, okay? The pressure has to go into the substance before it can be reflected at some level in the substance. We also know you can bounce it in the material itself. You can have the pressure moving in both directions and oscillate. So we know that the pressure can be high, and that high pressure can move around inside of something. So inside the balloon, for example, right? That's exactly what happens, right? So if I have any closed vessel, let's just say an air tank, and I put air in this way, I pump energy in this one direction, right? What happens to it? Well, it bounces off these surfaces, and now it will end up going in all kinds of directions. All of the bits of particles will eventually hit each other, bounce around, get all kinds of mixed up, and now it's the equal pressure in all these directions. So the pressure I put in one direction has now been diffused over the entire surface. So So I put in this much vector, okay, and now I have vector going in all these directions. Just a fact. And now I can let the energy out in any one of these directions. So I can completely change the direction of the energy by just putting in a pressurized vessel and then letting it out after I've allowed the pressurized vessel to equalize. Simple enough. So if the balloon slows down an incoming object on one side, so how does it slow it down? It has to deform. It has to absorb it as air pressure or, well, as pressure, period, right? Water pressure, doesn't matter. And it pushes also on the balloon. Now the air can just pressurize without making the balloon bigger, or the air can pressurize and make the balloon, both the air is pressurized and the balloon is bigger. So the balloon is now in a more stressed, elastic condition. So I've stretched the rubber band and compressed the molecules of air. And it will be, all of the energy will be in those two forms. But, you know, we could just use the hard vessel argument just as well and just say we're just going to compress the air. It will equally increase the motion of the object on the other side. So that's the argument, that no, it won't. Just because it applies pressure doesn't mean the pressure is used. So again, you can keep saying it, that pressure means motion, but it doesn't. If the other side pressurizes and says, I'm not moving, it's just saying, I pressurized, I'm equaling your pressure, and you're not going to move my atom, so the pressure is just going to stay high until something yields. But the wall is saying, I'm not yielding. If it pushes the incoming object back, well, that's what it's going to do because it's under high pressure, and as soon as there's any outlet, any place for the pressure to escape, it will escape. It will go that way. Okay, the object on the other side will gain equal motion in the opposite direction. So obviously there is no equal motion when you throw a tennis ball at a wall. The only equal and opposite reaction is the ball bounces in the opposite direction. But there's nothing else. The wall doesn't bounce anywhere, it doesn't go anywhere, it doesn't absorb anything. There is no action this way, there is only the action this way, because the wall merely said, increase my pressure, I increase it back. You have it back. It's as simple as just an elastic stick or something. I mean, it's just saying, go ahead, stress my molecules will stress back in the other direction. Done. We're finished interacting. This is just so not complicated. All right. About throwing the ball at a cart. Okay, so now we're throwing something at a cart, hitting it with energy. And we're saying, what can I expect to get back? So if the cart moves, my simple argument is, well, I mean, I could draw that one because that one's so illustrative of the canard they're trying to sell. You know, that's just such a pile of nonsense. So we'll do that one as a more visually undistracted drawing. All right, I have to remember how to do it. All right, so first, so we have the equal reaction. So everybody understands this one. Same mass hits another mass, and all you get is this. Okay, so motion in and motion out, and this one stops dead. So this one loses everything, and this one gains all of it. Okay, so that's the simplest. And then you just go this other way around. You say, okay, what happens when it's twice as big? Well, then I get 133 this way. Okay, what if it's 3 times as big? Well, then I get 150 this way. Okay, and so on, and so on, and so on, which is very bad. Sorry, little distraction. All right, and so theoretically I can go up to whatever a 6 mass, you know, who knows what the exact number is. I didn't do the calculation. I mean, twice the 4, okay, twice the 2 would be the 4, so that would be 166. And you'd say twice the 3 would probably be the 200, so 6 would be 200. All right. And that's their theory. Okay, so I have 100 in. All right, and these are the numbers I get out. And the funny part is, okay, as I increase the amount of energy I'm putting into the object, I'm also increasing the amount of reflection. So I'm going to get 33 reflection here, and I get 50 here, and then I get 100 back here. And obviously, if we go in the other direction, that is with lighter objects, okay, you could make the assumptions, okay, that, well, so what, does the opposite thing happen? You know, and obviously it doesn't, because they both end up going in the same direction, and that's the catch. So when they end up going in the same direction, all of a sudden the mechanics completely fail, and you don't get any of this nonsense. It's always just a total of 100. So whatever goes forward here, whatever this little bit of motion you get out of this thing, because the velocity of the lighter object won't be faster than the velocity of the thing hitting it. So it's going to have a small momentum, and the original thing will keep most of its momentum. So the lighter I make the object it hits, the more energy the thing keeps, okay? And it gives whatever the little tiny bit of extra. And, you know, that's the reality. So there's no consistency in the theory. It doesn't make any sense. It's just nonsense to say something, the heavier I make it, the more momentum I can put into it, because obviously wrecking balls would always do this. They'd always have one ball just standing there and hit another one into it, and then multiply how much energy they're pushing into the building. I mean, this simple pendulum idea would always work. You just put a static heavy object in the way, bang into the heavy object to make twice as much momentum. So any circumstance where you're using the momentum of an object to create energy, you know, torque, pressure, yeah, just put a heavy object in front of it, and you win. And you'll get some of the energy back, so you won't even have to lift the thing all the way back up again to hit it, right? I hit it with the wrecking ball, it bounces back, right? So I get my energy back, and then I can hit it again with the wrecking ball. Doesn't make any sense. It's nonsense. And did he counter that argument anyway? See, this is the problem with these comments, is they don't counter anything stated. So there's absolutely no use in having the conversation with them, because they have no obligation to pay any attention to what I have stated as a counter argument. And they just keep reasserting gibberish. So it is, as a practical fact, it's a waste of time. So there's some point where I just say, okay, time for you to go. Yeah, but you're not saying anything. What? Why isn't it connected? That is interesting. I have to pause because somehow I lost my comment section. Well, I did check the weather. Anyway, okay, so here we go. You know that if the cart is extremely light, the ball won't lose much motion. So I just pointed that out, that yes, when it's extremely light, it's not going to lose much at all, but they'll conserve all of the momentum. All right. If we make the cart heavier, the ball will lose more motion. Yes, and the cart makes more motion, collects more. So no surprise there again. It's all conserved. The same 100 before, the same 100 after. Okay, because momentum is conserved. The heavier cart is more motion will gain. So that's your theory, and it's nonsense, because that's obviously not what's happening. You can't make more motion than the object started with. That's the part that's just silly. Okay, and so again, he's taking the middle point and saying, because this works, it works all the way down, and it doesn't. You can't use the same logic, because once you're heavier than the object, you can't give it the same velocity, obviously. Okay. Luckily, the effect of bounce on force is something you can measure. So he's assuming that there's something in this video that disputes a single thing I said, which it doesn't. So I'll spare you the 12 minutes of annoying, kind of weird shit. I mean, they essentially have some they have some really weird drawings on a classroom wall. Teenagers don't, and you're just saying, no, I don't think so. But anyway, it's this new flipping physics thing, or whatever, that flipping physics guy. And these are actually his classroom videos, which are a little scary, frankly. But whatever, uh, as long as there's no touching involved, it's probably okay. Anyway, so I'll draw over the thing just because I feel like it. So all the video shows is him talking. He's a big fan of bicycle helmets. So he has a pressure table, okay, that just measures how much pressure is being applied. And he's just dropping a ball on it, okay, and bang, it hits he puts a diaper on it. So for whatever reason, like I said, a little bit weird. And he says bicycle helmet. So he's duplicating a bicycle helmet by putting a diaper on the pressure sensor. So he throws the ball drops the ball from the same height, okay, with the two things, and obviously, okay, like who disagrees? All right, number one, the ball bounces less high, okay, when it hits the diaper, obviously, and the pressure sensor detects less pressure. Duh. Okay, so, and obviously my argument is the diaper isn't an immovable object. That's the whole point of Kevlar, is to take threads and cause them to move in different directions and pull in all these different directions. So it spreads all the energy over a giant surface and creates a whole bunch of little micro movements, and that's how it absorbs the energy. It creates movement in material substance, and in some cases converts it even into eventually heat. So it's almost like a clay or something else. It's absorbing the energy, okay? So it's not going to move where you see the dent, permanent dent, but it's going to move in the sense that the fibers clearly pull against each other. They tear all their little fiberettes. They all kind of wiggle and wobble, and all of the energy some percentage of the energy will be absorbed by that. If I put enough of the pillow over the sensor, okay, all of the energy will be absorbed. So if you put a few layers, the pressure sensor will say nothing happened. So what does that prove? That's inconsistent with anything I have said. It proves nothing I haven't said over and over again. Now the experiment's a little bit interesting. Another one of his videos that I will, I guess, play. I'll show a piece of it anyway, because he's using a different pressure sensor, but at the same sampling rate. So it samples 1,000 times a second, and you think, okay, that's great. 1,000 times a second is a lot, but on the scale of a bounce, it's not that much. So it's really only 6 data points that you're going to get from the whole collision. So anyway, I'll find that. There it is. So he has this data. All right. So I'll just point out that. So all he did was drop a ball from 15 centimeters onto the pressure plate. Okay. So that's all he did. All right. And so the ball, okay, weighs 0.44 newtons. All right. That's what he established. Well, grams. Okay. And we know that 100 grams is a newton. So we know that it's, 0.44 grams, sorry. So we know it's 0.5 of a newton. All right. Because 100 grams so it's pretty close to 0.5, a little less, obviously. All right. So look at this key number. I shouldn't have drawn on this thing, I guess, but whatever. All right. So it's it's 50 grams, 44 grams of ball, and it's hitting this pressure surface, and it's registering the pressure. But so look at, let's see, this number here, right? Yeah. Oh, you can't see it now. Huh, strange. Anyway, 32. Okay, now it's actually, he's saying that this is a Newton reading. That's what it says, in newtons. Okay, so that's what it says, but it's not newtons. Okay, so he's got the decimal place in the wrong place. So 15 centimeters, you're not going to be able to create 64 times the weight. You can sort of understand, no chance you're creating 64 times the weight. It's just not possible. So he's got the decimal place in the wrong place, and it should be 0.2 newtons, which is exactly what I've been arguing. So, my argument is you go up 1 centimeter, you take a 0.5 newtons and you've doubled its mass. So now it's 1 newton. And you go up 4 centimeters and it's now 2 newtons, right? And then you go 16 centimeters and it's 4 newtons. So you can see 15 would be right about there. And since the actual object is only 0.44 newtons, you can understand that, yes, it's going to be a bit less than, okay, less than 3.9 or 3.8. It's going to be 3.2. So it almost comes out exactly as I have previously predicted it would, which I found gratifying. Gee, that is way over. I wonder what happened there. Camera must have moved. Is that what you're going to blame? Yeah, I'm going to blame that. I guess it should be in view. All right, I probably have to write with a better background. But anyway, the black doesn't work quite as well when there's other colors in the way. But it was good enough. I say it was good enough. So that's all he did. So I'm not going to play the rest of the video. I just wanted to point out he obviously in the spreadsheet he made a formulaic error and he has a wrong decimal point. And it's just kind of obvious that, you know, 1/2 of a newton can't drop 15 centimeters and weigh 32 newtons. That can't happen. All right. Yeah, so we'll go back to this slop, and we can get rid of this slop, and we can certainly erase that and read the last stinking rotten sentence. Let's see what it says, what his big finish will be, as he ignored everything I said in the video. And that's what he has literally done. He's ignored everything I said. All right, so just buy your own load cell or similar device. Why do I need to? I mean, what do you think it's going to prove? I mean, what argument are you saying? What are you saying? It's how much do you think it should weigh? I mean, he's already shown it working perfectly for my prediction. So, you know, except for his error, an obvious error. So what exactly is your argument? Do you think when you go twice as fast, it's going to weigh 4 times as much? And when you go 3 times as fast, it's going to weigh 6 times as much? I think you know it's only going to weigh 3 times as much. I think you know that. It's not going to be any obvious evidence that there's 4 times, 6 times or 9 times the energy. 3 times the speed, 9 times the energy. That's your theory. It doesn't show up on the pressure thing, so the pressure thing isn't going to say 9 times. It's going to say 3 times. So get one yourself, moron. And then you're still stuck explaining how, yeah, 2 units of pressure is 4 units of energy. That's what you have to explain. Oh, shit. Get yourself a stick. Okay? Tie a string to it and hang it from something. Right? So just tie a little string around it and hang it from something, balance it, and then start tying weights to the other sides and stuff, and you'll see that, yeah, kinetic energy is nonsense because momentum says completely different velocities equal each other. All right, anyway, compared to the money you get from a Nobel Prize, they are practically free. So that's my argument to your physics. You have all the prize money. I haven't gotten any my prize money yet. What do you think I'll spend it on when I do get it? Do you think I'll piss it away looking for neutrinos? What do you think, asshole? Who do you think would spend the money, science money, more rationally and logically? Them or me? What experiments do you really want to see? Do you think they're ever going to make a quantum computer shit for brain? Do you think they're ever going to do this stupid nonsense of trying to make energy by smashing hydrogen together? Yeah, no, they're not going to make energy doing that, retard. Oh, fuck. You got to break something to make energy, jackass. To release energy. Hydrogen atoms don't have any energy. They're the weakest form of atomic structure. The weakest. The least compressed. Shit. But anyway, fuck you. So I'll give you one more try, but I'm just, there's no point, right? You're demonstrating you're obnoxious to these lessons I'm wasting on you. You're paying absolutely zero attention to the reasoning and logic applied, and you're just insisting that somehow it's true. You can't show me any evidence demonstrating it's true, but you just keep insisting it's true. So until you show me something, until you show me somebody with an electric drill, okay, with an amp meter and a voltmeter, a watt meter, let's just say. And they run the drill twice as fast, and it's 4 times the energy. And then they run it 3 times as fast, and it's 9 times the energy. And then it's 4 times as fast, and it's 16 times the energy. And then it's 5 times as fast, and it's 25 times the energy. So show me that experiment. Or shut the fuck up. Because you have nothing. You have a fable. You're just a religious shit, talking shit. And how much of that is worth wasting your time on? Somebody who just keeps reading from the Bible and doesn't explain anything. I explain how the Galapagos Islands are volcanic, that they're all coming out of the same fissure and they're moving on a plate. Okay, so they're all created by the same fissure. All right, and it's just the fact that the crust is moving. Okay, and so the same volcano just keeps moving in a direction, essentially. So it just keeps remaking more and more islands, so to speak. And so there's islands that are very old, islands very young. Very interesting phenomenon, and clearly something that can't happen in 6,000 years. So if I'm discussing something with some moron who says the world is 6,000 years old, you'd say, well, why would God bother creating fake age? Fakely aging things. Get real, fucker. You're selling crap, all right? And that's all you are. You're just a defender of a flat earth theory, and you're just sitting here ignoring the evidence, ignoring the arguments, and just reading from your flat earth guidebook. And that's it. And that's just a waste of my time, frankly. You have no interest in the truth. You're belligerently an idiot, an asshole, a liar, and a fucktard. Fuck you.